Hello, Georgi Romanic here. Today we will talk about fictitious or apparent forces. These forces arise when we apply second Newton's law to non-inertial frames of references. So we need to first figure out what are inertial and what are non-inertial frames of references, and then we will mathematically extend the meaning of second Newton's law to these non-inertial frame of references. Inertial frame of reference is any frame that is at rest or is moving with a constant uniform velocity. That means if my tip of my finger is a base of a coordinate system and I use this to measure distance to this finger, then this is inertial. This finger is inertial coordinate system. If the finger is moving with constant velocity, let's say towards the camera, it is still inertial frame of reference or coordinate system. However, if this left hand, if this is the coordinate system and it is doing all kinds of crazy motion that contains acceleration, then it is non-inertial frame of reference. So non-inertial frames of references are those that experience some acceleration. That acceleration can be along straight line or it can be some circular motion. Originally, the second Newton's law was developed only for inertial frames of references. So if you ignorantly apply that law to non-inertial frames of references, then you will get wrong results. However, in today's video, we will extend the meaning of this law to non-inertial frames. You might ask at this point, why is this important? Well, think about it. In atmospheric sciences, we deal with air, and you take a mass of air and you reference it to what? Well, you reference it to the surface of the Earth. But remember, Earth is rotating. So inherently, Earth is non-inertial reference frame. So in order to apply second Newton's law to a parcel of air in the very exact and correct way, we actually need to use the form of that law of second Newton's law in non-inertial frame of reference. And today we will do that extension. At the end of this video, you will see that we will end up with 3 new forces, and these forces that appear when we extend the law to non-inertial frames are called apparent forces, because these forces are not physical manifestation of some underlying phenomena, but they are just accelerations that we observe if the coordinate system that we use to measure position of a particle is non-inertial, namely if it is accelerating. So let's dive straight into it, and then at the end of the video we will discuss a little bit more about these 3 forces. I will have a particle, let's say this one, and I will express position of this particle in respect to some inertial frame of reference, namely, let's say this frame of reference. And I will call this frame of reference I, which stands for the inertial frame of reference, and this will be x of I, or the position of this particle in respect to the inertial frame of reference. Now I will introduce another frame of reference here that is non-inertial. I will call it N, and this will be the position of this particle in respect to the non-inertial frame of reference. Namely, this over here will be x of n. This distance is x of n, or position of this particle in respect to the non-inertial frame of reference. This non-inertial frame of reference has unit vectors along the coordinate axis, And of course, the inertial one has 2, but I'm not interested into that one right now. So the position of this particle in respect to n can be written as x of n is equal xn1 e1 plus xn2 e2 plus xn3 e3, where e1, e2, e3 are the unit vectors along each coordinate of the non-inertial frame of reference. In short, I can write this expression as sum I goes from 1 to 3 xni ei. Now I want to express this position vector xi in terms of n frame of reference. What is that going to be? Well, x of I will be x of n plus what? Well, plus the position of the non-inertial frame of reference in respect to the inertial frame of reference. So I will call this the position, this distance, the position of n in respect to I, and I will call it x I n. So plus x I n. But this is further equal to the sum of x n little I e of I plus this x of I n. Now I need to, at the end of the day, get forces, so I need to start differentiating this with respect to time. I first differentiate this equation in respect to time to get velocity, and I will get here x I, this is x, sorry for my, over dt is equal. So I'm differentiating this equation. I will first differentiate this second term. It will be dxin over dt plus, I need to use chain rule for this term. So it will be sum. I first differentiate xni over with respect to t, and I copy ei, and then I copy xni, and I differentiate dei dt. But please notice that this is further equal to what? Well, this is just velocity of the non-inertial frame of reference in respect to the inertial. So this will be Vin plus, what is this? This is the velocity of the particle in respect to the non-inertial frame of reference. So this will be V of n plus, and I just copy the last term, sum of x n I d e I dt. To find acceleration, I need to carry out one more differentiation with respect to time of this equation, and then I will get d second x in inertial frame of reference with respect to time is equal. Well, I differentiate this one with respect to time. It will be acceleration plus, I will differentiate this in respect to time, dvn dt, and plus, here again I have to use chain rule, so I will have two terms, sum dxni dt dei dt plus sum x and I d second e I dt second. Now I will rewrite this term using chain rule once again. So this term is equal to what? Well, it is equal to the sum of dvni over dt times e I plus sum of vni d e I dt. As you can see, I used the same rule that I used above here when I was dealing with the differentiation of the position. Namely, this is the differentiation. Instead of position, I have velocity, so I rewrite this using the chain rule as the sum of these two terms. Now, I will just substitute this instead of this term here, and I will get that d second x I over dt second is equal to a I n, this term, plus this term. But what is this? This is just acceleration of the particle in respect to the non-inertial frame of reference, plus this term. But notice, please, that this term is exactly the same as this term, because dx ni over dt is just v and I, so I get 2 sum v n I dei dt plus, I just copy this term as it is. To find force, I have to multiply this by mass. And then I will get Fi, now this will be mass times this acceleration is the force. Fi is equal, I will first write this term, it will be Fn plus, now this term will be m Ain plus 2 mass sum of vni dei dt plus mass times this term x and this term x and I d second ei dt squared. Or I can write this in short and express in terms of forces in non-inertial frame of reference, that Fn is equal Fi plus this whole term Fapp, where Fapp in my notation stands for apparent forces. What are apparent forces? Fapp is minus of this. I am not going to write it for the sake of shortness. So this over here is the universal equation for the second Newton's law in non-inertial frame of reference. Namely, force with respect to non-inertial frame of reference is force in respect to inertial frame of reference plus apparent forces, and these apparent forces are these three terms. Now we will apply this general equation to the case of rotating non-inertial frame of reference. Namely, I am saying that this n coordinate system will not do anything crazy like move like that. It will simply rotate. And you can already see then from this equation that this term M AIN will disappear because there is no the change of position XIN between N and I coordinate system. Namely, this one will just rotate, it will not move around in respect to I. This was equation that we just derived for all apparent forces, and we said we will just look into the case of rotation, which means that this term can disappear and we are left with this term. So we need to find expressions for these two terms when we only have rotation. Okay, so I will take a coordinate system that is rotating. So this is my N, non-inertial coordinate system that is rotating with some angular velocity omega. The fundamental equation of rotation says that linear velocity v of any point is omega cross product r, where r is position vector of that point. This would be r. Now, this is one of the first equations that you learn in elementary school physics. So I'll take it that you know it. Well, I might as well quickly prove it. Let's say if I have some circular motion like that, where this is the particle is moving like that, and this is velocity v, this is the radius of the rotation, then the angular velocity omega is equal to 2 pi over t, where capital T is the period of rotation. But this velocity v is also equal to 2 pi r over t, because 2 pi r is the circumference of the circle, so it will complete one whole circle in the period t. But notice that 2 pi over t is omega, so I will get here omega times r. And this is the version of that same equation, but in the vector form. Okay, but what is v now when we go back to this equation? Well, v is dr over dt. So that is also equal omega cross r. And as Richard Feynman said in his first book on physics, if some vector equation works for vectors r, it has to work for any vector whatsoever. So I can use vector IE instead of r, and I will get here dEI dt is equal omega cross EI. Now, because I have second derivatives here, I need to differentiate this once with respect to time. And if I do that, I will get that d second EI over dt second is equal, well, I use the chain rule, it applies for cross product, d omega dt cross product EI plus omega cross product dEI dt. But please notice that dEI dt is omega cross EI. So I can rewrite this whole thing as d omega dt cross EI, this term stays unchanged, plus omega cross, instead of this I use this over here and I get omega cross EI. Now I am ready to substitute this into the general expression for apparent forces, and when I do that I should get F A P P apparent forces in rotating frame of reference are equal minus 2m omega cross Vn minus sum m d omega over dt cross xn and minus again sum of m omega cross product omega cross xn. All I did is substituted this over here, and notice that, for example, xni times ei will be actually the vector xn. The same is here for this term, and the same is here for this term. Okay, this, what we derived now, is the equation that gives us apparent forces in the rotating frame of reference. And we see we have three terms. This term is the Coriolis force. This term is the centrifugal force. This term is the Euler force. However, most of the times nobody cares about Euler force, because usually omega is constant in time and this term generally disappears. Now you know how to apply second Newton's law in any circumstance. You saw that we ended up with three additional forces, namely centrifugal force, Coriolis force, and the Euler force. In atmospheric sciences, we are only, and wind engineering as well as wind energy, we are only concerned with centrifugal force and Coriolis force. And these two forces will be covered in more details in the next two videos, where you will see under which circumstances we actually have to take into account the rotation of the Earth, and under which circumstances we can neglect to pretty good approximation the rotation of the Earth when we are dealing with parcel of air or any atmospheric phenomena. I hope you liked this video. Thank you for watching, and I'll see you in the next video. Cheers.